Hello everyone, this is Dr. Shahabuddin Ahmed. In this presentation, I will be talking about key principle of life cycle analysis with an example of hydrogen production. Now let us talk about what is life cycle analysis is. Life cycle analysis is a systematic analytical method that helps identify and evaluate the environmental impact of a specific process or competing processes. The input in life cycle analysis is raw material consumptions, energy, utilities. And output are emission to air, land, water, and waste. So what are the application of a product or process? Life cycle analysis has been widely applied to a product and process to compare and determine which product or process is most environmentally friendly. The second one is identify the weak environmental links of an overall product or process. And the final one is improve those segments of the life cycle to make it more environmentally friendly and sustainable. What are the benefits of life cycle analysis? So life cycle analysis is a promising tool for quantitative evaluation of the identify process cleanness, process comparison, for example, alternative process for the production, process ranking according to their environmental merits, process selections such that alternative treatment for sulfur dioxide emissions, and finally process development such that using centrifuge or filtration for solid-liquid separation. So there are some stages of a product in life cycle analysis, starting from extraction of raw materials, followed by product manufacturing, distribution, use, and finally disposal or recycling and reuse. Life cycle analysis has some concepts. First one is the cradle to grade basis, which is the entire life cycle of a product. Second one is cradle to gate basis, which is the raw material extractions to the product leaving the factory gate. Third one is cradle to cradle basis, which includes a recycling stage, for example, solar panel or wind turbine blade. And the final one is gate to gate basis, which is single manufacturing at a particular site, such that manufacturing of hydrogen using natural gas. So there are some phases of life cycle and standards. The first one is the goal and scope definition, which is conducted under ISO 14041. Under goal and scope definition, we have three things to consider. One is scope and purpose. Second one is system boundaries. And third one is the final functional unit. For example, the amount of CO2 emitted per kg of hydrogen production. So the functional unit here is the per kilogram of hydrogen. The second one is inventory analysis, which is conducted under ISO 14041. Under this category, all materials and energy resources consumed for the production of a product or process are quantified, and all waste emitted are quantified. The third one is impact assessment or classification, which is conducted under ISO 14042. In this category, inventory data are grouped according to categories of specific environmental effect or impact. The inventory data are then weighted to provide a numerical score. The final one is inventory interpretation of the results, which is conducted under ISO 14043, so that we can do the improvement in the process or product in the future use or future production. So let us discuss about goal and scope of life cycle analysis. So under goal and scope, the first one is define the organizational context of the life cycle study. So whether it is internal company use or external company use for public policy. The second was the purpose of the life cycle study. Is it to compare the competing products? Is it to identify major environmental burdens? Is it to make improvement to the processes? The third one is scope definition. We have to define the scope of the life cycle analysis. Under this category, system and its boundaries are defined. Data requirements, assumptions, details, and accuracy. These are the considerations under scopes. So here is the system boundary of a production process. The first one in the left hand side, you can see raw material and energy. And these are the processes in the plant operation, the plant commissioning, chemicals, electricity. So these are the raw materials, natural gas, water, coal, and biomass, for example. And the dotted line you can see is the system boundary. On the right hand side is the output, solid waste, for example, air emission, hydrogen, co-products, water effluent, other environmental interactions. So this is the system boundary of this system. Like input is raw material and energy, output is our, like in the right hand side as you can see, denoted by the raw arrow, and plant operation within the boundary, system boundary, consuming raw materials and energies. This is our system boundary. For detailed explanation, you can follow the link provided in that slide. So inventory analysis. What is inventory analysis? The second one we are discussing about in the life cycle analysis is inventory analysis, which is the purpose of inventory analysis to identify and quantify the environmental burden in the life cycle of the activity under study. The burden are defined by material and energy used in the system and emission to air, liquid effluent, and solid waste discharged into the environment. Inventory analysis includes the following steps: detailed definition of the system under study, data collection, allocation of environmental burdens in multiple function systems, and finally quantification of the burden. So what is functional unit? Functional unit is a measure need to be standardized. So energy use, for example, megajoule to measure the energy from non-renewable sources. Okay, the kilowatt hour, for example, for the energy, or megajoule to measure the electrical energy. So waste materials and emission measurements, for example, tons to measure airborne emission and solid waste. For water, and the final one is standard basis for comparison, for example, per product piece or per kg of product. What's need to be included in the raw material extractions? For example, we include energy and then waste and emission to air. This is the output. Energy is our input. Similarly, energy is our input, waste and emission are our output. In the transportation phases, we discussed these 5 steps in the very first beginning of the presentation. So these are the inventory analysis. During inventory analysis, in all of these stages, we have to account energy and emission and waste for each of the processes. For example, raw material, production, transportation, use, and disposal. So the third one is the impact assessment phases. So in that phases, first one is classification, and in under classification, aggregation of environmental burden to a smaller number of environmental impact categories to indicate their potential impact on human, ecological health, and resource depletion. Second one is characterizations. Third one is normalizations, and fourth one is evaluation. We will discuss these things later. So under the classification of impact assessment phase, inventory data are assigned to category according to their impact. For example, CO2 emission contributed to the greenhouse effect are assigned to global warming potential. So this is the impact assessment classification. For example, global warming potential. This is one of the impact category. Eutrophication is another impact category. Acidification is another impact category. And these are caused because of the nitrogen oxide. Okay, and CO2 mainly is responsible for global warming potential. That's why this CO2 is generally classified under global warming potential category. We will discuss a little bit more in the next few slides. Okay, so this is the classification of impact assessment. Very important slide to understand. So global warming potential, what causes the climate change? Okay, so second one is impact category is acidification potentials. So this causes acid rains. Photochemical oxidation potential, so this causes smog. So non-renewable resource depletion, consumption related to indexed scarcity. Ozone depletion potential, emission with potential to harm ozone layer. Eutrophication or nitrification is pollutant that increase the nutrients and lead to loss of dissolved oxygen. Human toxicity, emission with potential to affect human health. And ecotoxicity is emission to toxic substance to damage flora. So for a detailed analysis or a detailed discussion, you can head to this link and we can see this global warming potential for different emissions. But here in this table we can see, so there are two global warming potentials from different sources, two sources in fact. So CO2 global warming potential is one in each of the time horizon. For example, 20 years potential, 100 years potential, and 500 years potentials. So methane is, for example, in 100 years potential, if I discuss, so in one category it is 25 times severe than CO2, and another category is 21 times severe than CO2. Let us discuss about the red one. So this is just nothing but from different sources or different environmental bodies, international environmental bodies. So this means, this 21 means, so this emission, methane emission, is 21 times severe or harmful than CO2 emission. However, nitrous oxide is 310. That means this nitrous oxide emission is 310 times severe or harmful, more harmful than CO2, and so on from different other emissions. Now let us do some math. How we can calculate the global greenhouse gas emissions from combustion of fuel, for example. Okay, so the typical formula for this greenhouse gas emission calculation is from combustion of one kilogram of fuel, for example, is EIJ. So EIJ means, I means the combustion of fuel, kilogram of fuel, I, and G represents the emission or greenhouse gas emissions, is equal to QI. QI is the quantity of fuel in ton or kiloliter or etc. And EC, I means fuel, and EC is energy content of that fuel. For example, gigajoule, ton, or kiloliter, and meter cube, etc. So, and EF represents emissions of GHG from J, like J might be CO2 or nitrogen oxide, etc. from the combustion of fuel I in kilogram of CO2 equivalent per gigajoule of fuel energy. So EC in the subscript refers to the fact that emission are per unit of energy content of the fuel. EC is energy content, okay? And EF is actually emission factor, like this amount of CO2 is generated per kilogram of per gigajoule of energy by the combustion of, for example, like one kind of fuel. So if I discuss these units, it will be more clearer to you. So QI represents the quantity of the fuel. It can be kilogram. Okay. For example, I have put it here as a kilogram. For example, coal. 1 kilogram of coal, and the energy content is represented in gigajoule per kilogram of coal, for example, and an emission factor of that coal is kilogram of CO2. Ij is representing combustion of I fuel, and J representing the CO2, and per gigajoule of that energy. So if you rearrange these units, you can see kg gone, gigajoule gone, and then emission is kilogram of CO2. Okay. Now one thing to be noticed here, there are some in the subscript, you can see OXEC. So this OX represents oxidation factor, because when you combust fuel, that does not basically burns entirely. Some portion remains unburned. For example, in here I have given the typical data. For example, for solid fuel we use 98 to 99%. For liquid fuel 99%, and for gaseous fuel it's 99.5%. For simplification, you can consider 100% oxidation. Then you don't need to consider this oxidation factor for the simplification, simplified cases. And of course, in the denominator, you can see 1,000. So that means if you have a kilogram and you are converting it into the ton. Hope this makes clear. Okay, let us do some calculation here. So we will calculate global warming potential for the emission of multiple greenhouse gas emissions. So each GHG quantity is multiplied by that global warming potential, which I discussed before. Like global warming potential for CO2 is 1, for methane is 21, for nitrous oxide is 310. So we have to consider those things here. So this is based on Kyoto standard value. In the red mark, we wrote the table in the previous slides. And then okay, let us do some calculation here. So for example, we have a facility that emits 100 tons of CO2, 5 tons of methane, and 1 ton of sulfur hexafluoride during a reporting period. And what are the total global greenhouse gas emission for the year in CO2 equivalent? We have to calculate in CO2 equivalent. This means equivalent, which is very important to understand. Like we have to multiply the emission factor, global warming potential emission, global warming potential factor with the emission. For CO2 emission, for CO2 emission, multiply with global warming potential, which is 1, of course, and then we can get 100 ton of CO2 equivalent. So this equivalent comes from the multiplication of the global warming potential. The second one is 5 tons of methane. Okay, so 5 tons of methane, amount of methane or amount of emission multiplied with global warming potential. So we have 5 tons And we saw the global warming potential in the previous table, that for methane it's 21. That means it's 21 times severe or more harmful than CO2. So that makes it 105 ton of CO2 equivalent. Okay, so the third one is sulfur hexafluoride. So emission, how much? It's 1 ton, and global warming potential for this one is very, very high, which is like 24,000. So multiply with this one, 23,900 ton of CO2 equivalent. Now let us sum up all those three. The total GHG emission is 100 for CO2, 105 for methane, and 23,900 ton of CO2 equivalent from the sulfur hexafluoride. So altogether, so 24,105 ton of CO2 equivalent. Okay, so this is some of the data for different kinds of fuels. For example, natural gas energy content is 39. Emission factor for this one is 51.2. For methane, it's 0.1, and etc. For brown coal, bituminous, coking coal, diesel, etc. So these are the data we need while calculating our global emission and global warming potentials. And if we are given electricity, and so the global emission factor for the electricity differs from area to area, country to country. I have given the emission factor of the CO2 per gigajoule of energy in Australia and different states of Australia here. So now we will calculate the global greenhouse gas emission from combustion of fuel. Okay. Okay, so now let us assume 100,000 tons of lignite or brown coal are burned in a power station. Looking up this fuel in NDER, which is I forgot the total. It's national inventory, something like that. So determination method, which you can just go through this link, and you can find the NDER value in schedule 1 part 1, but we have been given the data here. So our energy content for that lignite is given as 10.2. This value you can find from these sources. Per ton of fuel, 10.2 gigajoule per ton of fuel. Okay, so and emission factor for CO2 is 92.7 kilogram of CO2 equivalent per gigajoule. So now we can convert this amount of lignite in terms of gigajoule, like how much energy we are getting. Just need to multiply with this one. And one thing to be noticed here, so this emission factor, this E represents the global warming potential. This 92.7 is included, the global warming potential is included already with this 92.7. So emission factor for the methane is 0.01 kilogram of CO2 per equivalent per gigajoule of energy. And finally, the emission factor of nitrous oxide is 0.4 kilogram of CO2 equivalent per gigajoule of energy. Alright. Now, so now let us calculate the emission of different emissions from burning of 1 ton of lignite. Okay, so emission of CO2, just amount of fuel, which is, you can see in the right hand side the equations. QI is the amount of fuel, EC is the energy content. So amount of fuel, this thousands, this 10.2 is the energy content, and emission factor. Emission factor is given as 92.7 for CO2 and divided by thousands to make it ton. So that makes it 945.54 ton of CO2 equivalent. Similarly, for methane, we can calculate it 1000 amount of fuel, energy content of methane 10.2. It should be okay, yeah, 10.2 for the lignite, and emission factor is given as 0.01 divided by thousands. For nitrous oxide, amount of fuel, energy content, emission factor divided by thousands, 4.08. So now sum of all those things, all those three, that makes you 949.72 ton of CO2. Now this way you can calculate how much emission one of the plant is emitting. For example, one of the power plant, for example, if one of the power plant is burning 1000 ton of lignite per year or per month, something like that, then you can easily calculate how much CO2 it is emitting, or how much CO2 equivalent is it's emitting from the reporting period. Now let us calculate another method, which is the liquid fuel, and we will learn something different from this slide as well. So, for example, a steam boiler combusts 1000 kiloliter of fuel. From sampling and analysis, the following fuel properties are found. So this is the properties. In the property, carbon is 88.1% weight percent. Okay, and the density of the fuel is 850. Energy content is 40.1. Okay, so it's a liquid fuel. So let us consider the oxidation factor, which I discussed before, is 99%. So first of all, we have to calculate the emission factor. So how we can calculate emission factor? Emission factor is carbon content in the fuel. Okay, so it's 88.1% divided by 100 means percent, making it percent. Oxidation factor multiply with 3.664, which is coming from the molecular weight of CO2, how much carbon it has, dividing by 12. If you do the unitary method, then you can easily calculate how much carbon, how much CO2 we are generating from burning of this amount of carbon. Okay, so the emission factor we have found 3.19. Okay, so emission factor in energy basis 3.19 multiplied with 40.1, which is the gigajoule per kiloliter, and divided by density, which is 850. If you rearrange the units, you can see the unit is coming as 3 kilogram of CO2 per gigajoule of energy, which is our aim to find. Okay, so now we have 1000 kiloliter of fuel altogether, and our emission factor. So this emission factor we have calculated here if it is not given, but in case if it is given, for example, we found from NGER website or in their database, then in that cases you don't need to calculate this emission factor. So now the amount of emission by burning of 1000 kiloliter of fuel, we can just use that formula, like QI is the amount of fuel, and 67.8 is our emission factor, and 40.1 is our energy content, and of course divided by 1000, making it tons of CO2. Okay, now we will do a case study for hydrogen production using wind turbine process or wind turbine system. So the goal, first of all, we discuss these things. This is a case study. I will follow step by step. So goal and scope of this: to identify and quantify the environmental burdens in the life cycle of the renewable hydrogen production via wind and electrolysis. Like electricity is coming from wind turbine and putting into the electrolyzer to make hydrogen. So we will do that analysis under cradle to grave basis with a functional unit of 1 kilogram of hydrogen. So these two lines, if you go to the previous slides, you will be able to understand what it means. Like I have defined the goal, what is the scope, cardinal to what is the basis of our study, and what is the functional unit. So many things are included here. So this is my system boundary. System boundary, as you can see the dotted lines, my material and energy is our input at the top, as you can see. On the right hand side is hydrogen, use of hydrogen or hydrogen production. This is my output, and another output is emission to the environment. So, and these are the processes, for example, manufacturing of the electrolyzer, power plant manufacturing and evaporation for the electricity, water extraction, and we considered here the disposal as well. So there are 5 steps we discussed, like manufacturing, extraction of raw materials, production, transportation, use, and disposal. So these are the 5 steps we discussed in the very first beginning. So we considered the disposal unit in disposal steps as well here. So, and there are some steps here: electrolyzer for the production of hydrogen, and that hydrogen is then compressed and then storage. So this is the entire system, and this is our system boundary, and we will do the analysis now. So the second one is inventory analysis. The goal and scope definition is done. The second one, as you can see, is our inventory analysis. So inventory analysis, this is the most critical one. So if we can do these steps as accurately as possible, then your life cycle analysis would be more accurate. So we have manufacturing of turbine and its operation. These are the processes. We have electrolysis system, we have the storage system. So these are the 4 steps we have considered here. Okay. So if you want, you can consider other steps as well. But for simplification, we are considering these 3 steps here. So for manufacturing of turbine and operations, what are the resources or the raw materials required? For example, we need 145.4 kilogram of coal. Our functional unit is 1 kilogram of hydrogen. Sorry, it's not kilogram, it's a gram. So how much iron we need is 136. So these are the data you need to collect from different sources. This is the summary of the data. So now iron is 91.8 iron scrap. Limestone, how much required? 353 gram. Oil, how much? 36.8. So water, 10,446. Okay. So now this is another important things to understand, like carbon dioxide. How much carbon dioxide is emitting by burning of 145.4 gram of coal, and this amount of other resources. So how much emission it will generate, and if we can easily calculate using the different steps I showed in the previous slides. Like you have to just calculate how much energy content you have, how much fuel you have, what is the emission factor, and if you go to the database, you can find the emission factor for different fuels as well. I have given you some data in the previous slides. Okay. So now we can calculate how we can calculate or we can collect the data, like using, if you use this amount of resources, what is the amount, what are the amount of carbon dioxide, carbon monoxide, methane, and so on we will be generating for manufacturing 1 kilogram of hydrogen. So for the electrolysis process, similarly, this is the amount of coal you have to burn, this is the amount of iron you need to use. You might ask, like, what is how we can calculate the emission from the iron, right? So iron is not a energy, or iron is not giving you energy. But so to make iron, you know how much CO2 it is emitting. So then on top of my head, I can understand that if for 1 ton of iron production, you are emitting 2 ton, at least 2 ton of CO2. So then you can easily calculate from 12.5 gram of iron production how much CO2 you are generating. But you add up with this carbon dioxide 41.8. Some portion is coming from iron, some portion is coming from coal, burning of the coal, and so on, etc., etc. And for the storage, coal, iron scrap, limestone, and so on. So for the production of iron scrap, limestone, so these are the some resources you are not directly emitting, but for the production of those components or those materials, you are emitting CO2, you are emitting nitrous oxide, methane, and so on. And these are the direct emission, which is natural gas, burning of natural gas, burning of oil, and this water is like collection of the water from using pumps, etc., etc. So these are not the direct emission. So some are the direct, some are indirect. And you can, for each of the process or each of the resource used, like coal, you are emitting carbon dioxide, carbon monoxide, methane. Not necessarily you are burning coal and producing CO2 only, but rather you are producing carbon dioxide, carbon monoxide, methane, and so on. So now for the coal, you sum up all those three: coal, and coal from these three. How much coal you are using, how much iron you are using, how much iron scrap, how much limestone, natural gas, oil, and water. So this is the sum of all these three. And you sum up the emission, how much carbon dioxide you are emitting from different systems or different processes. Just to sum up, like 741, 41, and 166, that comes up 950. And similarly, in sum of all these components of the emissions or the emissions and sum it up here. So now this is called inventory analysis. Okay. So this table I have already shown in the previous slides, but here I have already again put it here to make it more clearer to you. So for example, here global warming potential for CO2 is 1, for CO1 methane is 21, nitrogen oxide 310. Okay, so these are the measured GHG emissions from for the production of 1 kilogram of hydrogen. So as we saw in the previous slide, how much CO2 is generated for the production of 1 kilogram of hydrogen? 950 gram. So we will make it equivalent CO2 emission, CO2 equivalent emission. And to do that, you need to multiply with global warming potential, which we discussed before. So multiplying 950 into 1 is 950. And for the CO, it's 1 again, and multiply with this one, make it 0.1, 0.9. For the methane, 0.3, and we know the global warming potential for 100 years potential is 21, makes it 6.3. Nitrous oxide is 310, makes it 15.5. Altogether, it's 972. So now we can say that for the production of 1 kilogram of hydrogen, we are emitting 972 gram of CO2 equivalent per kilogram of hydrogen production. Now the last one is interpretation of the results. So in previous slides we saw manufacturing. So these are the 4 steps of the process we considered in this study: manufacturing and operation of the turbine, which cost the total energy of 606.6 kilojoule per kilogram of hydrogen production. Electrolysis process required 436 kilojoule of energy, and hydrogen compression and storage required 2,875 kilojoule of energy. So altogether we required 9,919 kilojoule of energy for the production of 1 kilogram of hydrogen. So which is equivalent to this amount of CO2. We can easily calculate, like using the previous formula, like amount of fuel multiplied with the energy content. So we have already got the energy content, so you don't need to multiply with the amount of fuel. So just multiply the emission factor, okay, and then divided by 1000 to make it like, if it is in kilogram, then divided by 1000. If it is not, then you don't need to. We can keep it like kilogram of hydrogen, gram of CO2 equivalent, or if you want to convert into the ton or kilogram, then you can do that. Now we do the interpretation of the results, like here you can see in the 3 categories how much energy is consumed. 67% is consumed in the manufacturing of the turbine. So this is 6606 or 6606 kilojoule of energy out of 9,919 is 66.7%. So now in the results, or the interpretation of the result, in the discussion, we can say that 67% of our energy is consumed for the manufacturing of the turbine, the manufacturing and operation of the turbine. 4% required for the electrolysis technique, and compression to 29%. And while discussing of the CO2 emission equivalent, which sector contributed which amount of CO2? Of course, higher the energy content, more the CO2 emission, and we can see 78% is responsible for the manufacturing of turbine and operation, 4% from the electrolysis, and 18% from the hydrogen compression and storage. So this way we can discuss our results, or explain our results. Okay, so this is all about what we can do manually in our calculation, and there are some commercial software which is like CIMAPRO or GABI for life cycle analysis. For the detailed life cycle analysis, easily you can calculate how much CO2 you are generating, and what process we can do the comparison, and we can do different impact categories, for example, human health, ecosystem, resources. Using this software, you can easily calculate for any like any of the processes if you have the inventory data. For example, this one I have calculated for the production of hydrogen for manufacturing or production of 1 kilogram of hydrogen. This SOEC, solid oxide electrolytic cell. There are different methods we know for the production of hydrogen. I calculated all those most of the hydrogen production processes and compared the results with each other. So as you can see, solid oxide electrolytic cell, and this one in the bottom is the proton exchange membranes, and this one is the PB, and the solid oxide electrolytic the grid electricity, and this one proton exchange membrane with the grid electricity, steam methane reforming with CCS, and the bottom one is the coal gasification with CCS, and the right hand side this one is steam methane reforming with using without CCS, and this is coal gas without CCS technique. So these are the results from the SIMAPRO analysis. So you can use SIMAPRO. Probably in the next presentation or the next lecture, I will be talking about how we can use the SIMAPRO software for our lifecycle analysis. So for further reading, we can go through these resources to better understand what are the technical terms or different acronyms. So for example, I discussed about this database, like how we can calculate the emission factor. I derived or I collected this data from these sources. And these are the emission factor of global warming potential CO2 particles 100 years lifetime, for example, is here, and different data I have presented in my presentation are collected from these sources. There are some videos here as well. You can go through this YouTube video for better understand the life cycle process. And as I said, in the next presentation or the next talk, I will be probably talking about how we can use commercial software, for example, SIMAPRO or GABI, to calculate our CO2 emission or global warming potential from different product or processes, for example, hydrogen production, as I discussed. Thank you for your time. I'll see you next time.